So large N theories, that's actually been probably for me the most dominant topic of research. I've been in this field since the early 80s, actually, and large N is kind of very, since the paper of Hoft, especially in 1974, on large N limit of gauge theories. There has been a lot of work on that, and actually even before there was a lot of development on large N limits in statistical mechanics. And recently I've been working on a new type of large N limit, which is called tensor large N limit. And prompted by that, I wrote recently lecture notes with Fyodor Popov, who is my current graduate student, and Grisha Tarnopolsky, who is a former graduate student, now a postdoc at Harvard. It's rather strongly focused on this tensor large N limit, but also introduces the other two sort of more traditional large N limits. So these are the lecture notes, and this is the archive number. So I hope you look at that. I probably won't be following this so much, but I think it will be a useful resource. Okay, so a lot of what I'll be saying will be about critical phenomena. So you basically, one thing that I will be assuming that most of you have read a standard quantum field theory book, right? Like Peskin and Schroeder, for example, is a particularly good resource. And one thing that is completely, basically, ubiquitous is this. So, for example, if you take a 4D QFT, quantum field theory, you can either think about it as in Minkowski signature, which is then we think about three spatial dimensions and time. And then you can do a Euclidean continuation, for example, do Euclidean continuation. Where we send time to I times x naught, and then we get a 4D Euclidean field theory. And this is actually a lot of what people are doing now is basically in this domain, where we think about this is where you describe naturally critical fluctuations. So this is, for example, leads us to statistical applications to statistical mechanics and things like that. So of course, if you are a particle phenomenologist, you are working in this, typically in this dimension and this signature, and then you study things like S matrix, right? So there is S matrix for signals. Once you go to the statistical mechanics, you tend to study correlation functions at different separated points. Correlation functions where you average over different configurations. So in this Euclidean signature, we have the Euclidean path integral, integral z, which is integral over field configurations phi e to the minus s, right? And the most standard thing, for example, that a lot of Peskin and Schroeder is devoted to is taking s is equal to, so this Euclidean action turns out to be integral d dx times 1/2 d mu phi squared, right? And then you have plus 1/2 m squared phi squared plus some lambda over 4 factorial phi to the 4. Right, and in this Euclidean theory, you can study many interesting things. So you can. So in fact, this also can describe real world, just like this. So you can think of this theory in two ways. You can often, like when this was introduced, say in the 70s or 80s, you just say, well, this is the simplest quantum field theory we can think about, and you say that this is you can say this is a toy model for Higgs, for the Higgs boson. Of course, Higgs has a more complicated interactions, but people actually initially weren't even sure if there are any elementary scalar fields, so this was basically just a toy model. But then if you are a person working on statistical mechanics, this is actually not a toy model. It's a model that describes real world on the nose. And the setting in which it describes the real world on the nose is, for example, the vicinity of critical point in the water vapor phase diagram. So water and vapor are the most commonly known substances, right? And and we all know that that at pressure 1 atmosphere, so here you have water, right? Here you have vapor. And this is the temperature, right? And here you have ice. And we all know that at standard pressure, 1 atmosphere, the water, this transition happens at 100 degrees, right? So if this is not drawn on to scale, but this will be like 100 degrees. Right. And we all know that if you start increasing the pressure, then the water starts boiling at higher and higher temperature, and this is essentially because the vapor gets more and more compressed at that temperature. So the distinction between water and vapor kind of starts getting smaller and smaller, and then eventually you reach this amazing. This is the critical point. So this is this famous critical point where the distinction between them just disappears. And here we have this continuous or second order phase transition. This goes back to the legendary paper by Landau from 1936. Which started kind of the path that many of us are still following. This eventually led to the notion of conformal field theory, and so on. Okay, so it turns out that the vicinity of critical point is literally, in real world, described by this theory with d equals 3. D equals 3. Then this describes water critical point. Now, do most of you know why? Do some of you know?
So in the lectures of Misha Stefanov, he actually described this, so why this was the case.
Okay. So he talked about the Ising model.
Yes.
I see. Okay, so right. So this is sorry, I was not aware of this, but yeah. Yeah, so I'm starting where someone has left off, I guess. This is by no means like my end point of my, so now that you know this, you also know that there are these, did he talk about ON magnets?
No.
Good. I have something new to say, finally. Okay, so, Right, so this theory as a quantum field theory is actually very difficult in dimension 3, the physical dimension 3. So one thing that actually to connect to what Misha Shaposhnikov was just saying, if you just draw this as a classical potential, right, then we have, so the essential point is that for m squared bigger than 0, that's when you have t bigger than tc, and the classical potential looks just like this, right? Classical potential looks like this, and then you have the unique vacuum, and this is essentially like being on this side. There is absolutely no distinction between the two phases, the water and vapor phase. But then when you go to m squared less than 0, then you have this double well potential, which is one of the most commonly studied systems, right? And then there are two classical configurations here, right? We can just call this, so phi is equal to plus or minus a, right, in this case. And this corresponds to t less than tc. And then the critical phenomenon happens when we, so to reach criticality, reach critical point, we tune m squared is equal to 0. Okay, and in 3 dimensions, this actually is widely believed to give us a scale, basically a conformally invariant field theory. So there is a special range, basically for, let's just say for d less than 4, this gives us conformal invariant field theory, or at least scale invariant field theory. Theory. Okay, now if you do this, so if you think of this as just double well in quantum mechanics, is this possible in quantum mechanics? Yeah, basically, we all know how to solve the quantum mechanics and double well potential, and then we know what the ground state is, right? The ground state will not favor one over the other, right? So for example, in d equal 1, which is the quantum mechanics case, you don't get a critical behavior due to the fact that there is this instant-on tunneling that Misha was just mentioning. So the ground state looks like this. Ground state will be just something, will be an even function, right? This is psi as a function of phi. Right, so then in quantum mechanics, you think of this as just the position coordinate. This is double well potential. So you see that there is absolutely no preference between being here and here, right? And then the first excited state will look similar to this, except it will be an odd function. So it will be just crossing over at 0 here and still. Now, in the semi-classical regime, they're split only very slightly by the instant-on tunneling effect, but they're still non-degenerate, right? The fact that they're non-degenerate means that that there is no true critical behavior in quantum mechanics. Another sign of it is that if you go to the pure phi to the 4 potential, you don't see anything particularly special happening. Right, you don't see some kind of accumulation of dense states near the ground state or anything like that. So in the upshot is that these critical phenomena are very dimension dependent. So in quantum mechanics, quantum mechanics, basically, especially double well, there is no critical behavior. But, and this, maybe I will end my lectures with this, if you consider some appropriate large N quantum mechanics, then you can have critical behavior. And you can have a notion of symmetry breaking and so on. So all of these standard notions need to be sometimes revised if you go from a system with small number of degrees of freedom to a system with a large number of degrees of freedom. So this may be possible in the large N limit. And actually, my most recent piece of work is a quantum mechanical model of a large number of fermions, large number of interacting Majorana fermions, that exhibits this kind of Z2 spontaneous breaking of Z2 symmetry that appears, for example, in higher dimensional field theory. I won't yet tell you like exactly how this works, but this is possible in this. It's not actually in these lecture notes, but I'll try to mention the basic idea. Okay, so now, right. So now, since I started talking about large N, so you know this whole story about Ising model, right? So you think of this. This is also the three-dimensional Ising model, right? I won't. So the Ising model, we just think about some lattice, right? Let me just draw the lattice. And on each side you have some Ising spins, sigma, and these are just. So sigma just takes values plus or minus 1, right? So you can have plus, plus, minus, minus, plus, right? And the energy functional is just equal to minus some j times sum over nearest neighbors ij, sigma I, sigma j. And then, so since Misha Stefanov talked about this, you basically know roughly what happens, that if you look at 0 temperature, right, there are two minimum energy states, plus all pluses are, so at t equals 0, there are two minimum energy states. States which are all plus or all minus. And then once you turn on the temperature, there will be thermal excitations where, say, among all pluses, some will flip to a minus, right? And then there will be more and more of this, and then eventually you reach some configuration where you reach this critical point. And in the vicinity of this, so for example, in d equal 2 and 3, so in d equal 2 and higher, then you actually find there is a critical temperature. There is a critical value. Beta j critical, where you get this long-range correlations and nearly scale invariant system. From what I understand, Ising, actually in his thesis, he only studied the d equal 1 model, where that's an exactly solvable model where there is no phase transition. And later it was generalized to d equal 2 and higher. And this is in some sense the most ubiquitous statistical mechanical model, the most elemental statistical mechanical model where the degrees of freedom are just pluses and minuses, right? It exhibits second order phase transition in 2 and higher dimensions, but starting with 4 and higher dimensions, this theory is sort of boring in the sense that it's all its critical exponents are just free field critical exponents. Do you remember from? So there is a strong dimension dependence in this business. Do you remember why from previous lectures why this happens?
IR divergences.
Hmm?
You get IR divergences in Xi that correlate.
Well, it's if you consider doing perturbation theory, for example. So why does Peskin and Schroeder mostly consider the case of 4 dimensions, right? The classic case of 4 dimensions, because in d equal 4, this coupling is dimensionless, right? This means that this 5-4 is a marginal operator, right? So in you have this picture of RG flow here. So this is treated as a UV Lagrangian, right? So you have RG flow from free UV theory, UV theory to some interacting IR theory. IRCFT. So this is only the case in d less than 4, right? Because just in this free UV CFT, the dimension of the phi field is equal to d minus 2 over 2. d minus 2 over 2. And in particular, in d equal 4, is just 1, right? So phi to the 4 in weakly coupled theory has dimension 4, which makes it a marginal operator, right? But if you go to d above 4, right, this phi to the 4 actually has higher dimension than 4. So for d bigger than 4, this operator is irrelevant, right? And what this means is that its effects will simply wash out as the theory flows to the IR, and you get just free field, essentially free field theory. But in the physical dimension, dimensions of interest, which are d equal 3, which is actual phase critical point in this room, or some 2-dimensional samples, there are very strong coupling effects associated with this operator. So you see that for d, in a nutshell, this is for d less than 4, operator 5-4 is relevant, right? Relevant in the RG sense. If you are rusty on this, just look in Peskin and Schroeder. I think this is one of the books where, for example, I think chapters like 12 and 13, they go over this whole story of Euclidean continuation and critical phenomena and discuss some of these concepts. So in particular, for d, if you are in d equal 3, this lambda is a dimensionful coupling constant, and its effects grow as you start sort of coarse graining the system. So far in the infrared, you have you have very strong effects of the interaction, and we don't know how to solve the theory. Now in D equal 2, so in D equal 2, if you go back to the glorious days of theoretical physics, Onsager actually solved this theory on a lattice. Okay, so there is a celebrated Onsager solution, which then was simplified in various papers, and then eventually in the then it all culminated with this paper by Belov and Polakov-Zamolodchikov, the BPZ paper, which exhibited actually a solution of a whole general class, so-called conformal minimal models, of which this Ising model in German you have to remember to say Ising. In which Ising model is the first example, and it has the central charge C is equal to 1/2. The miraculous thing is that the theory is really exactly described in some sense by a massless Majorana fermion. So there is some mapping of this critical behavior. And this is highly non-obvious, but so this is C equal 2, which is the massless Majorana fermion. And as a result, we actually know the exact scaling exponents of various things. Like we can compute how the spin-spin correlation, the correlation function of two Ising spins will fall off with distance through these exact solutions. But life is much harder, actually. So there is something special, and this is due to some infinite symmetry, some enhanced infinite symmetry of two-dimensional critical theories. And I won't talk so much about this. But in the recent years, a lot of attention has been devoted to the D equal 3 case. So in the D equal 3 case, we don't appear to have any exact symmetries, and the whole story is very complicated. I would say this is a kind of, so the D equal 3 Ising model has for years been considered one of the holy grails of theoretical physics. So in the D equal 3 there is no exact solution. But there is a variety of very precise information that's known. And how do we know this this information? Well, there are several roots. Some are classic. Well, there are several classic roots. And right, so basically you can do the following things. There is something called the Wilson-Fisher epsilon expansion.
So can I ask?
Yes.
This
Yeah.
is D equals, so you mean 3 plus 1?
No, I mean 3 Euclidean dimensions. You can also think of it as a 2 plus 1 theory, but continue to Euclidean space. Okay, so here, I skipped over this step, but maybe I should say why this is 3 dimensions. Just think about a cubic lattice and think about Ising spins on the cubic lattice. Average over many spins, right? So this field, so if you have, for example, D equals 3 lattice, in D equals 3 lattice, you just define the field phi as a kind of average value of this sigma, averaged over some large number of spins. So you're sort of coarse graining the system. The whole notion of RG has to do with coarse graining. where you average over many and many lattice spacing. I cannot give a course on RG because that would take many lectures, and I think this is like a absolutely crucial development in theoretical physics. It started with people thinking in approximate terms about lattice models and so on. Right, so one thing that you can, for example, do in this 3D lattice model, just think about the correlation function where you average, say, over sigma at some position I here, and then suppose you go to some far away and have some position sigma at position I plus little n, where n is large, right? And you want to know how this falls off as n. So the idea is that in this near critical temperature, it falls off as n to some power minus, let me call this 2 delta, delta times e to the minus this n times the correlation length, xc. Sorry, n divided by correlation length, xc. And then you can tune this correlation length, so as t goes to tc, so at this value, the correlation length, which gives this exponential fall off, basically goes to infinity. Okay, and this, precisely how it goes to infinity is one of the so-called critical exponents. Once you've dropped this term, once this went to infinite, you have just the power law scaling. And that's the idea of how this works. Now, when you think about when this happens, you can afford to average over many and many large domain, right? And then in the language of this quantum field theory, if you average over a large domain here, you obtain the following Euclidean notion. We basically have the Euclidean two-point function of phi of x, phi of 0. Right, and this will be in three-dimensional Euclidean space, where here we have a three-dimensional Euclidean lattice, here you just have three-dimensional Euclidean space. This will go like 1 over absolute value x to the power 2 delta, and then e to the minus x divided by xc. Okay? So did I answer your question? Basically, this phi is like an average of spins on this two-dimensional Euclidean lattice, three-dimensional Euclidean lattice. There's no time here. We're just doing this appearance of quantum field theory is not like the one that we have in particle physics. It's a very different route, right? But it's another application of quantum field theory. Now, many of you probably heard this term, quantum criticality. That's the condensed matter, people use it a lot. So there are some two-dimensional materials. I mean, the one that you hear about all the time is graphene, right? It's just one layer of graphite. It's an inherently two-dimensional material. That is amazingly enough described by 2 Dirac fermions. But there are more complicated materials, and these can sometimes be described by a theory in 2 spatial and 1 time dimension that is essentially a Minkowski continuation of these type of theories. So that's another appearance from. So there are also, besides just the familiar water vapor stuff, there can also be so-called quantum critical systems. Quantum critical systems on a plane. On a plane. So they lead to actually 2 + 1 dimensional QFT, quantum field theory. So this is another appearance of quantum field theory that has nothing to do with elementary particles. You just have some complicated chemical compound, and miraculously, in some regime, it's properly described by. And as I mentioned, there is, of course, the four-dimensional idea of a Higgs, but that is actually will be somewhat different from what I want to do. As I mentioned, I want to go slightly below 4 dimensions. Okay, if you are in exactly in 4 dimensions, there is this theory is not critical. Do you know what happens with this theory if you try to tune it to criticality? It's far from trivial question because, you know, there is this legendary Wilson-Kogut review called Renormalization Group and Epsilon Expansion. And a large chunk of it towards the end is devoted to the question, is there critical behavior in 4 dimensions? Like in this sense, in the 4 Euclidean dimensions. And this was actually just a few months before that question was sort of answered, but there is a fundamental obstacle to finding critical behavior in 4-dimensional theory, which I will mention in 1 second. And this has to do with RG flow, right? So, so let me yes.
So you were just saying that we don't have an exact solution in 3D, but some of this epsilon expansion.
Right. Yeah. So the epsilon expansion idea consists of the following, and this ties into the question of 4D behavior, is to what they said is work formally in D equal to 4 minus epsilon dimensions, where epsilon is much less than 1. Okay, and then what happens is that this interacting, so in 4 minus epsilon dimensions, so if you look at what happens to this IRCFT, it's actually weakly interacting in D equal to 4 minus epsilon. And this is essentially explained in Peskin and Schroeder, for example. Okay, so I'll come back to this in 1 second. But then so this is one route. Okay, and recently there is also some technique which dates back to the 70s, which has been revived about 10 years ago by Rычkov and collaborators, called Conformal Bootstrap. And this has so far led to the most exact determination of these critical exponents. And then the third is the 1/n expansion. So let me just talk a little bit about this 1/n expansion, because this probably will save me a bit of time to discuss all these concepts at once, where I have a theory where I can do both the epsilon and the 1/n expansion. And this is basically the following then. instead of this Ising spins, let me talk about the so-called classical ON model or ON magnet. The ON magnet. And this amounts to the following. Take on each lattice side the degrees of freedom, which are little vectors in n dimensions. Here, let me draw them in just 2 dimensions. But so we have a bunch of these vectors. Okay, so at each side have a vector. N-dimensional vector. So n is basically, and it's also unit vector. Unit vector, n is n1, n2, ... and absolute value n. Right, such that sum of ni squared from 1 to n is equal to 1. And then the energy functional is taken to be analogously to the Ising model. Namely, we take epsilon E is equal to minus j times sum over nearest neighbors ij and I dot nj, just the dot product of them, right? And then the statistical sum is z is equal to sum over all these configurations of these vectors on the lattice e to the minus beta j. Okay, so this is nice, right? So when n equals 1, you just get back to the Ising model, right? Because then n is 1, there is only one component whose square is 1. And this is a real vector, so for n equal 1, you basically get that n1 is equal to plus or minus 1, and you get back to the Ising model. For n equal 2, your vector is just living in 2 dimensions, right? It's just, so everything is just specified by one angle, right? And this people call the O2 model or the O2 model, or people also call it XY model. This also plays a huge role in statistical mechanics, this XY model. In particular, this model describes the superconductor to normal state phase transition. So it's, in fact, there were some very precise experimental determination of critical exponents of this model from a satellite experiment, which apparently are turning out to be slightly wrong, but just for experimental reasons. Right, and then for n equals 3, you get that's the O3 or Heisenberg model, or 3 Heisenberg model. So these are and this also, like, this essentially you can think of some molecules with spin, right? And these spins with 3-dimensional spin. So these describe the spin vectors classically, and then they interact with some kind of exchange interactions, and you get this type of Lagrangian. Okay, so all these models, so if you go to d equal 2, okay, so Onsager solved the case n equal 1 for us for solution of the n equal 1 model. Then for n equal 2, the model turns out to be actually very special. And it has some interesting phase transition, something called BKT, Brzezinski-Kosterlitz-Saulis transition. There are some vortices related to solitons that Misha talked about, and so on. But then for n equals 3 and higher, actually the model turns out to be not critical in d equal 2 for some peculiar quantum reasons. So there is no criticality. This has to do with the fact that in d equal 2, this model is described by a nonlinear sigma model, which has a quantum violation of criticality. But in d equal 3, all these models are critical. Okay, so these ON magnets for these ON magnets, and in particular in d equals 3, all of them make sense. All have second order phase transitions. Phase transitions. And moreover, this actually shows some dramatic simplification for when n is sufficiently large. In fact, so as n goes to infinity, the theory simplifies dramatically. Theory simplifies. So this, I think, is the first example of how this large n simplification can occur. Okay, and just let me just show you what. So, for example, I'm interested in this. How at the critical point this delta, the power with which the spin-spin correlation is gonna decay, right? In this case of this ON vector model, the field phi will now have a label, right? So we have the averaged value of an I you identify with some scalar field phi of x, right? Then we're going to have phi I of x with phi j of 0. There will be some delta ij, which has to do with just ON symmetry of the problem. And this is called the delta phi, 2 delta phi. Okay. Now, similarly, we can, let me erase all this. Okay, so now how do we adapt this path integral to describe this theory? We basically have now this label I. Here we will have phi I squared. Then here we will also have phi I squared. And here we traditionally write it with somewhat different normalization. We basically have g over 4 times phi I all squared, right? And this is sufficiently important model that it made it to many textbooks. In particular, this model is described in Peskin Schroeder chapter, I think 12, 13. And there is tremendous exploration of this model in the 70s, right? Okay, so what is the? It turns out that this 1 over n expansion can be developed analytically, okay? And you have the following structure of results. For example, in d equals 3, you find the following answer. For example, suppose you want to know this delta phi. This delta phi is equal to 1/2 plus some series, okay? Eta 1 over n plus eta 2 over n squared plus dot dot dot. Okay, now one general bad news, like in any quantum field theory, the expansions tend to be asymptotic. So it's not a convergent expansion. So this will be some, so the coefficients after a while will start blowing up. And you even can see it from the explicit calculation. So for example, in d equals 3, you find the following results. And they're completely analytic. Plus 4 over 3 pi squared n minus 2256 over 27 pi to the 4 n squared. And at this point, the next term, n cubed, is looking more complicated. There are some transcendental numbers in it, like zeta of 3. But this is just to make the point that here you have the analytic answer to basically what appears like a strongly coupled problem, right? Now, if you so in some sense, this is the dream of a large n person, is to develop something like this analytically. It's possible for this model, for reasons that I will sort of talk about more generally. In this ON magnet, this is called the vector large n limit. The vector large n limit. And this has to do with the fact that this field phi has only one label, okay? You see that the interaction phi I squared is just a square of an ON invariant quadratic operator. Okay, so it's and this is just dictated by ON invariance. There is nothing else that you can write down. Right, and basically, so the phase transition that we're discussing is what separates the phase with positive m squared and the negative m squared, right? Like you have to tune the mass to 0. Again, I think Misha has demonstrated this champagne glass potential, right? Where, for example, for n equal 2, right, you have to imagine taking this. So for n equal 2, what does the potential look like, right? You have, and you have to imagine rotating this, right? So n equal 2 is the first case where you get the Nambu-Goldstone boson. For n equal 1, which is the Ising universality class, you just have a breaking of a discrete symmetry, right? For high temperature, there is a unique ground state. For low temperature, there are two ground states, plus and minus. But already for the O2 model, there is a continuous circle of ground states. So you get this circle, so ground states, continuous set of ground states, but set of ground states parametrized, which is parametrized by the sphere in n-1 dimensional sphere, right? For n equal 2, it's S1. For n equal 3, it's S2, and so on. And we're studying this sort of transition right where this is about to happen, right? This is the whole. So I think Landau understood this picture very well. He basically created this picture of second-order phase transitions. But in the 50s, people, and even early 60s, people did not fully understand that these critical exponents actually are hard to calculate for some range of dimensions. Like they become easy to calculate in higher dimensions. For example, in 4 and higher, this operator is just irrelevant, and then you'd get these free field critical exponents. So, so for example, if you go to dimensions higher than 4, so in general, you actually have the following picture. So this delta phi will be d minus 2 over 2. This is the free field critical exponent plus some eta 1 of d divided by n plus eta 2 of d divided by n squared, and so on. Okay, and just a sort of conventional picture is that for the standard phase transition, if you go, so for d greater than 4, there is just a mean field critical exponent, and these corrections vanish. I will actually, some of the work that I did over the last few years ignores that, and I'll maybe say a few words about this, but the mean field critical exponent, which is delta phi, is equal to d minus 2 over 2. And for this, there is even in some cases, there is rigorous mathematical proof of this fact. This is something mathematical physicists love to do. They derive bounds, right. I will actually say that in some sense, this is not completely trivial like that, but I may come back to this. But just coming back to stuff that's well known for sure is that for d less than 4, it's not that simple, right? And this is something that Landau and his collaborators initially did not know. Like even this whole picture started emerging in the 60s and kind of culminated in the 70s, this picture of corrections to these infrared critical exponents. Now there is, from the point of view of this epsilon expansion, there is a very simple way to see why these corrections appear, okay? And this has to do with the amazing invention in quantum field theory called the beta function, right? Okay, so you all know, you've all studied how to compute beta functions. So for this particular field theory, if you look at beta g, so let's go back to just perturbative QFT. QFT in d equal 4. Right there, we have that beta g, which is just the derivative of g with respect to log of this sliding scale. This is the Kalman-Semantic beta function. And you get the following answer, which is n plus 8 divided by 8 pi squared times g squared. Okay, and of course we also have some higher loop corrections. By now people went to 6 loops, I think at least, like plus. So all these coefficients are known, but the crucial thing is the following, that if you start with a weak coupling, right, and flow to the infrared, namely reduce log m, then the theory will just flow to 0 coupling. And this is called the triviality of 5-4 theory in 4 dimensions. So you basically see that in d equal 4, you get triviality. Namely, the massless theory will just flow to 0. G goes to 0 in the infrared. And if you read this Wilson-Kogut review. I highly recommend it. Basically, it lays out this apparatus of renormalization group, which is has been extremely influential since that review. But then, so this is the crucial invention that was made by Wilson and Fisher around 1972, which is to think about it slightly below 4 dimensions. Let's just imagine reducing. So in 4, therefore, you don't get a non-trivial interacting CFT. Not in any simple way. And the answer is that with scalar fields, you just don't have it. Not even fishnets. But if you go to 4 minus epsilon dimensions, then you get, just for trivial engineering reasons, you get this term minus epsilon g. Right? This is because the operator just becomes slightly relevant and you have this additional term. Right? Then if you plot the beta function as a function of g, you get the following plot then. So this is beta and this is g, and you find the following 0. So you find that just solve this equation, right? So beta equals 0 has 2 solutions. And you find that g star is equal to 8 pi squared divided by n plus 8 times epsilon plus order epsilon squared. Okay, and the crucial thing is that this interaction strength in this epsilon dimension is small, right? It's suppressed by epsilon, right? And so this is the G star, and if you look at the flow lines, basically this is an IR attractive fixed point, namely you approach this fixed point as you flow towards the IR. So this is what you call the IR attractive fixed point. And this is present for all n. So this is IR attractive. And then you can basically substitute this value. So the apparatus of epsilon expansion is to substitute this value of g into the anomalous dimensions of the operators phi and phi squared, which are well known. This is again done in Peskin and Schroeder. And then you get actual physical information. So you find, for example, that this delta phi is equal to 1 minus epsilon over 2 plus n plus 2 divided by 4n plus 8 squared epsilon squared plus order epsilon cube. And then there is the scaling dimension of this operator phi squared, which is also a very important notion in these theories. And you get that you get the delta I squared 2 minus 6 over n plus 8 epsilon plus order epsilon squared. Okay, so this was the big breakthrough, and people use it all the time. But and this is a great technical tool. But there are some troubling things about it. So it works very well for scalar theories, but for scalar theories, for other theories like fermion, sometimes there is no unique or elegant way to really continue the theory, say from 4 to 3 dimensions. Like, for example, the dimensionality of fermion representations can jump and so on. And also, like Slava Rычkov and collaborators have been complaining recently that the theory in 4 minus epsilon dimensions per se is not fully unitary. There are actually violations of unitarity. Like if you look at some high enough dimension operators, they violate unitarity bounds and so on. So it's a kind of technical crutch, but it's not totally clear. It's fundamental enough or fully defined enough, right? Like there are some issues with how well-defined theories in continuous dimensions and so on. Is in continuous dimension. Nevertheless, it has been used very successfully, so for theories with n equal, basically, so there is this famous range for d for 2 less than d less than 4 for theories with ON models. These ON models with n greater than 2, namely O3 and higher, you actually can develop both the 4 minus epsilon and 2 plus epsilon expansions. The 2 plus epsilon, so in that case, you also have, you can develop both both 4 minus epsilon and 2 plus epsilon expansions. And then you can just sort of imagine like working in this range. Like you have, this is d, right? This is d equal to 2. Say this is d is equal to 4. You basically know some function in the vicinity here, right? Then you also know it sort of here. And then you can, and the thing that you're most interested in is somewhere in the middle. But you can sort of do some somewhat ad hoc things called pade extrapolations or Borel pade or all kinds of tricks. And you can get like pretty good information about what's happening here. I mean, this is the hard region. The d equal 3 is both where it's sort of from nature point of view, it's a very interesting region, but it's rather hard. Okay, then you can of course also do just lattice simulations, right? Just lattice Monte Carlo simulations, for example, for the Ising model, and let me just list a few data points. So this can be done for different theories. So maybe I should pause to ask if there are questions. Yes?
Here, where you define delta phi squared, what is the first term here? In the upper right corner.
Oh, the first term.
This one.
Yeah, this has to do with. You're asking why it's 2.
So it's a 2.
Yeah, it's a. Oh, sorry. I thought you were asking why it's 2, but I mean, from this point of view, it's. Yeah, in 4 dimensions, phi has dimension 1, so it will certainly be 2 plus some small corrections, right? And yeah. So just a few numerical results. Okay.
So just to make sure I understood, so you were saying like, going 4 minus epsilon and 2 plus epsilon? Like we have to do 2 plus epsilon to make it more well defined, right?
No. I think some people, I think initially Wilson and Fisher were just doing 4 minus epsilon. Okay, 4 minus epsilon is a well-defined expansion for this Lagrangian. Essentially, and there is a completely iterative procedure for doing it. The more loops you compute, the more terms of higher order of epsilon you get. Yeah, and this is actually, people are still working on this. Like, for example, here, I don't have it written down, but there is some function of n, like f3 of n times g cubed plus f4 of n times g to the 4, and so on. And you can grind out these corrections here to, for example, to this operator to higher and higher orders. It's technically very challenging, but I think I've seen paper in the last 2 years that did it at 6 loop order. Okay, so they computed the 6 loop beta function, and then you get terms up to order epsilon to the 6. The problem with this is that this expansion, the coefficients and the expansion start getting larger. This is a chronic issue with perturbative quantum field theory. So there is a problem with, we know that at high order, at order epsilon to the n, the coefficients, you expect this 2n factorial behavior of the coefficients. And this is just the divergence of the problem with divergence of perturbation theory. That's why people can persevere for 5 years and get one more loop, but it does not immediately, you cannot basically take this raw expansion, plug in epsilon equal to 1 and get anything close to real answer. So you have to do so-called resummation of perturbation theory. Now, the way people do resummation is, one of them is the so-called Padé extrapolation, where so the Padé technique is, if you want to do, you just do something very naive. You say, let me get this function, say delta phi of epsilon, right? And it's a ratio of 2 polynomials, like say order p n of epsilon and order pm of epsilon. And these are 2 polynomials. Okay. That helps a lot. But what also helps is if you happen to know what the answer is exactly at d equal 2. Okay, and sometimes you know what it is in d equal 2 from the Onsager exact solution. So for example, for the Ising model, you actually know. So for n equal 1, you know that this, if you plot delta phi, you know that miraculously this happens to be equal to 1/8 from this exact solution. While here it's equal to 1, right? And you're looking somewhere in between, okay? Now people have, can be a very useful input because you also fix the value at d equal 2. And one, there has been sort of a group of people working along, and there is, for example, a book by Hagen Kleinert. If you want to see some many orders in epsilon, you should read this book. H. Klein, he has various incarnations of this book that he keeps updating, and collaborators. I think Verena Schulte, Flolinda. That's one version that I actually have read. It's available online, and it talks about up to order epsilon to the 5 expansions. They get actually, after some massaging, they get extremely good value here, in excellent agreement with Monte Carlo. So basically, what you get from this, so you have to shoot quite far, right? It varies from 1 to 1/8. But you find that in, for example, the data for 3 dimensions, it's something like this. So you find that for n equal 1, so this is n, and this is delta phi. For n equal 1, which is 3D Ising model, it's 0.51813 ... Then n equal 2 is 0.519 0 ... 3 it's 0.51875 7 4 is 0. So the interesting thing is that you see it's hovering pretty near 1/2, right? It does not go too far from 1/2. And this is far, far from obvious, right? Because this is really supposed to be a strongly interacting theory. In non-interacting theory, it would be exactly 1/2. So you flow what seems like a long way, and you end up not far from where you started, it seems. And this is sort of one of the reasons why large n qualitatively works, because in large n expansion, this first term is unambiguously 1/2, and the corrections are of order 1/n for reasons I will explain in a second.
Where do the numbers come from?
So these numbers, I think these just come from a mix of different determinations. Monte Carlo.
They're not like from these
They are, yeah.
Okay, so how do you do this? I mean, where do the polynomials come from?
Oh, you fit the coefficients. You suppose you know the expansion to order epsilon to the 6, right? Then you have these different versions of Pade. You can take, say, the 4th order one here and the 2nd order one here, or 3 and 3, or 2 and 4.
But there's no good reason. You just do it and fit it and see what happens.
Yeah, that's the criticism is that this is rather ad hoc. It's not rigorous. So people play with these things. And this is what if you want to read a lot of detail, there are also some souped up versions where you first do a Borel transform and then Pade it and then Borel transform back. So it's a bit a mixture of art and science. But when you do it in many different ways, sometimes you have like a bunch of different ways give you pretty consistent results, and they also give consistent with Monte Carlo. There is also something called Conformal Bootstrap, which has allowed to get a couple more significant digits here in a totally different way. So, and that's a big breakthrough in a way if you are into precise determination. But this epsilon expansion in the end agrees well with Monte Carlo. But okay,
Sorry.
yeah.
So the second order phase transition is something that like you kind of like do with different methods, and then you all agree that it's going to be second order phase transition, right?
Right. Yeah, you can, for example, if you just simulate these spins on a lattice, right? You just simply sample these spins randomly and start varying this critical temperature, like you vary the beta J. Okay, and then you see that in the vicinity of some point, you see that the domains of spins get very large, and you can measure the correlation lengths on the lattice, and it starts like dramatically increasing in the vicinity of this critical temperature. And people do it very precise, like you can do some so-called finite size scaling, you repeat it for bigger lattices. And
so from lattice, it's supposed to be second order phase transition, so you you then like say, oh, then these two like extrapolations should meet at a certain point. Maybe not the same slope, but like, yeah, is that how it is?
Yeah. I mean, there is some presumed smooth function there of dimension, and this whole like, so it's like a bag of tricks. You have this dimensional continuation. From quantum field theory point of view, the idea is that you just, the question is, can you tune this m squared to 0 consistently? And the answer is yes. Yeah, and then what you have is a consistent quantum field theoretic description of this second order phase transition. But the presence of these extra terms means that this quantum field theory is very complicated, and you have to really care about what. The bad news is the following: that if you actually look at the size of these corrections for n equal 1 or 2, they're really huge. So this 1 over n expansion does not work so well for low n models. It does not work as well as epsilon expansion. So these corrections, so this 1 over n, and this actually is said already in the Wilson-Kogat paper, this coefficients get smaller, coefficients small for n starting with 8. Starting with 8, you get like actually excellent agreement between the numbers that you get, for example, from Monte Carlo and this and these corrections.
One question.
Yeah.
Stepanov, when he described this enormous dimension of the phi field,
Mm-hmm.
so he explained that one reason it's somehow surprisingly
Small.
deviation from 1/2 is that the
Mm-hmm.
self-energy diagram starts at 2 loop. So at only at 2 loops.
That I think by itself does not. It's a. In fact, the full reason is not well known. Is not fully understood, I would say. Yeah, if you look at, I mean, suppose you did the 2 loop and the coefficient was large, then you immediately it would bury this epsilon expansion. For example, if you just write down the coefficients for where did they do this? Yeah, so if you look at this, I have the coefficients for n equal 1. For n equal 1, you get n equal 1. You get 1, delta phi is 1 minus epsilon over 2. And here you suddenly get epsilon squared over 108. I'm not sure we a priori expected such a small number. And then the next one is actually epsilon cubed times 109 over 108 squared. And it turns out that these numbers are so small that if you just include these 3 terms, you get extremely close to 0.518. This is a real strike of genius, right? Wilson somehow knew how to get things right. And so this just with these 3 terms, if you set epsilon equal to 1, you get 0.518. Yeah, if you just drop this term, you would not get so close. So this is like an ideal user-friendly epsilon expansion. And in particular, this term here drops you from 1 to 1/2 right away, and further corrections are small. There are lots of theories where this simply doesn't work. Like this correction will be suddenly large, and you already have to pade, and then you basically don't know, right? But from large n point of view, in spirit, you immediately get 1/2 as the leading term. And then you have to, the bad news is that these coefficients are not so user-friendly for small n, but they start behaving for larger n extremely well, actually. And in fact, with Bootstrap, we were able, like, yeah, if I could show slides, I would show this. Maybe I'll just draw.
It's possible.
Yeah, I could show next time. I could actually start next time with a couple of slides, because it's very impressive. It's both a check of this Bootstrap and a check of the 1/n idea, which only became possible recently. Because I think people did not bother so much with these higher n theories on a Monte Carlo level. I mean, they're harder to do, and but the 1/n correction sort of starts behaving very well for 8, 9, 10, 20, and so on, and you get a very precise agreement. Okay, and then, so how do we do this? Why is this 1/n expansion so nice? Like, I mean, you know why epsilon expansion is nice. At least I can calculate all these terms if you know how to renormalize a 5-4 theory, right? It's just a matter of computing these beta function coefficients, but how does this work? And so that's one thing I wanted to, I probably have to finish up soon, but in a nutshell, you can rewrite this action with the help of an auxiliary variable. Some people call it Hubbard-Stratonovich transformation. You essentially can replace this action by the following one. So you introduce the path integral is now z. You can rewrite it as d phi I, and then d sigma. Sigma is the auxiliary variable, e to the minus s sigma. And then the action s sigma is integral d dx times 1/2 d phi I squared minus I over 2 sigma phi I squared plus 1 over 4g sigma squared. So sigma is just the auxiliary non-dynamical variable here, right? So it's just an identity. You do the Gaussian integral over sigma, integrate it out, and you clearly will get this term, right? You'll get the term phi I all squared, right? But then in this form, so this trick was invented, I'm not totally sure by who. I think Wilson was one of the people originally involved, but then there are many people working on this. Then you actually, this field sigma acquires so-called induced dynamics. That initially it's non-dynamical, but it acquires dynamics through the loop of the phi field. So this is sigma, and then there will be a loop of phi field, right? And moreover, the coefficient of this term is of order n, right? Because there are n fields contributing to this loop. And this gives us some very concrete tool for doing the calculation in this theory. You first compute this loop, you get this term of order n in the effective action for sigma, and then you basically then treat sigma as a dynamical field. And the correction to delta phi, for example, this correction, just comes from attaching sigma loops to the phi field. So this will be the phi 2-point function, and you have this type of diagram. Now, since this will be of order n, this diagram here will be automatically of order 1 over n, right? Because you get the effect, so induced effective action will be some sigma integral d dp, sigma of p, sigma of minus p, times some function. First of all, there will be this trivial term, 1 over 4g, plus some function of p. Okay, so there are two things. First of all, this function is of order n. This function will automatically be of order n. And moreover, the behavior of this function is such that that it will dominate at low momenta. Okay. In fact, you find that this is some. Let me just write it down.
Automatically of order n?
Because there are n fields running around the loop. You just this phi I has a free index, right? So phi 1 makes the same contribution as phi 2, as phi 3, up to n, right? So you get automatically n. And then you have to evaluate this integral. This is a pretty simple exercise. If you want a simple review of it, let me give a reference to a paper I know well, which happens to be by me. But it's by no means original. It's like a review. And it's a paper by, let me write down. So this technique is reviewed. A paper by Lin Fei, Simone Giombi and me. And you can easily, it's 1404 dot, I can predict, but this is good enough. It's the archive number that you can find from, but you can find this paper. It's 1404. And it basically explains how this computation works. I mean, this diagram is completely trivial in position space, right? Because these are just free propagators, and then you Fourier transform it. And then you get the following function. So this sigma p sigma minus p, this function f of p, which is multiplied by n, behaves like this. It's some c tilde, which is a dimension-dependent coefficient, times p squared to the power 2 minus d over 2. Oh, sorry. Sorry, I meant, oh. No, here I meant the opposite. It's d over 2 minus 2. Yeah, this is what you get in the effective action. And then there is some actual gamma. Let me just write down the full d-dimensional answer. 2 to the d, 4 pi to the d minus 3 divided by 2, gamma of d minus 1 over 2, and then sine pi d over 2. Just some dimension-dependent stuff, but the crucial thing in this business is the following, that you see that when d is smaller than 2, this goes like a negative power of p squared. D is smaller than 4, this is a negative power of p squared. So this dominates over this 1 over 4g. So you can, at low momenta, you can just drop the 4g, this initial term. Okay, so this term you can drop in the p going to 0 limit. And this immediately gives you a kind of, it's a very non-trivial technique, which allows you to compute straight off. It's a kind of resummation of perturbation theory, which allows you to compute straight off the 1 over n corrections.
What is written in the lowest now?
The lowest. Yeah. So this is the effective action. This is basically just this diagram in momentum space. Sigma of p, sigma of minus p.
There's a lot of
Yeah, let me just rewrite. Yeah, the first term is just 1 over 4g, right? So if you, let me just write this again. So the induced dynamics for sigma. Dynamics gives us the following. So it's integral d dp, sigma of p, sigma of minus p. There will be 1 over 4g plus n times some function of momentum. Okay? And this function I wrote down here. Okay? And then you see basically, so first of all, you see that you want to scale, so the large n limit should be taken with gn fixed as n goes to infinity, so that these two terms are comparable. That's a standard thing about this vector large n limit. But then something dynamical happens for d less than 4, which is this term dominates over this term at low momentum. And then we can just use this term and basically drop this term. And this is what allows us to compute these corrections actually as a function of d. But I better stop now. But so this, you see, and this actually is a very nice technique that also has been used to check higher loop calculations, because you can then take this. These are two different expansions. One is in powers of 1 over n for any d. The other one is exact in n, but only in d equal 4 minus epsilon. So they have to be mutually self-consistent. And this provides some interesting checks on, for example, 5-6 loop calculations and so on. But I'll continue tomorrow. Okay. Questions or? Yes.
So over there for large n extension, are those coefficients numerically solved, lattice, or it doesn't matter?
Yeah. Well, this is the analytic technique from exactly what I'm doing here. Yeah, this is from doing these diagrams with the sigma field. This is how they are obtained, and completely analytically. Then you can just take, for example, suppose I take n equal 10, and someone has worked out from Miletti's Monte Carlo for these 10-dimensional vectors. This is certainly, you have to Monte Carlo many numbers, but then you can try to compare, for example, the results that this formula gives with that. Yeah, the numerical one thing. Yeah, if you look at, it's not obvious from this, but the numerical coefficients here are the following. So this is really 1/2 minus or plus 0.135 divided by n minus 0.097 divided by n squared. And then already the third one is 0.94 divided by n cubed. So if you're doing it for n equal 1, first of all, you immediately see that this is already very big. And then you have to do some kind of resummation. And this really is huge already compared to this. So this is an example of a not so well-behaved series if you're trying to solve the Ising model. But if you plug in n equal 10, you see that this will produce big suppressions. And then you can compare, for example, the first 3 terms, and then it works very well.
Okay.
Mm-hmm.
We can break for lunch.
Mm-hmm.
So thank you again.
Okay.